Hello, my name is Mickey Vollenhofer. I am in the Organic 2 class, and today is July 2nd, 2026. So I will be here talking about my reaction mechanism analysis, and I will be going over like the vinylithium reagent as well as the alpha beta unsaturated ester, which I did in a recent assignment. And with that, I will be going over the curved arrows, basically representing its electron flow, and then talking about the role of the aesthetic workup. And then towards the end, I will finish up by talking about its regiochemical preference as well. Yes. So for identification of key components, I will be talking about the nucleophile as well as the electrophile here. So the vinylithium reagent is basically a nucleophile because of its carbon-lithium bond, which is basically very highly polarized. And with that, the carbon carries out the significant electron density, which makes it a strong, hard nucleophile. And then on the other hand, here, the the alpha beta unsaturated ester. It is a very electrophilic site because of its carbonyl carbon, and because of that, it has both inductive and resonantial effects that come from the oxygen atoms. And because of this carbonyl carbon, it's therefore like a primary site of attack. So now mechanism step one here is the nucleophilic attack. As you can see, like I said, I'm going to talk about the curved arrows. And then yeah, so there. First, we're gonna talk about the nucleophilic attack, and then we're gonna talk about the electron movement in the carbonyl, and then finally the formation of the tetrahedral intermediate. So first, I drew a curved arrow basically from the nucleophilic um, vinylic carbon to the electrophilic carbonyl carbon, basically representing like the formation of creating like a new carbon-carbon bond. And at the same time, the pi bond of the carbonyl pi bond, uh, has to break in order to avoid like exceeding carbon octet, to exceed the carbon's octet. And then I finally draw the second arrow in order to from like the carbon oxygen double bond, like basically to the oxygen atom, basically letting it being able to like create and produce the tetrahedral intermediate. So when it gets to that stage, the previous carbonyl oxygen, it basically gets ends up carrying a negative charge, giving me like an alkyl oxide intermediate. So now for mechanism set two, the collapse and elimination. So talking about collapse, um, because the tetrahedral intermediate, it's not really stable after it was created, so the reaction has to continue. So the lone pair on the negative charged oxygen, it ends up collapsing back in order to reform the carbonyl double bond. And with that, I represented it with a curved arrow from the oxygen to the carbon oxygen bond. And because the carbon, it can't have five bonds, so it ends up forcing the methoxide leaving groups to like split apart and depart. And with that, I show it with like another curved arrow, which indicates like the cleavage of the carbon oxygen bond, like the beginning of the split. And with this step, it's driven by the reformation of the strong carbon oxygen bond, oxygen double bond. Now for this one, I'm going to be talking about the acidic workup here. The acidic workup, basically the meth oxide ion, it picks up a proton in order to create that like methanol. And this step I basically have here, it shows like it neutralizing the reaction mixture in order to like stabilize the final product, which can finally give us this ketone here. So for the electron flow principles, it's basically dictated by two main like driving forces, which is the electrostatistics and the thermodynamics. I'm stuttering here, sorry. So this electrostatistics here basically it has a high electron density, which is the nucleophile, and it seeks out low electron density, which is the electrophile. And then now the second main driving force here is the thermodynamics, which is basically the reformation of both, not both, sorry, of the carbon oxygen double bond, which is very like highly exothermic. And with that process, the double bond is basically significantly stronger than like just having a normal single bond. Now for the regiochemistry and the stereochemistry, the reason why vinylithium ends up attacking the carbonyl directly instead of like performing a conjugated addition is because of like how vinylithium is a hard nucleophile, as stated before. These hard nucleophiles are basically charge controlled, and they basically favor like direct 1-2 addition to the carbonyl carbon, while softer nucleophiles, like such as like the Gilman reagents, they tend to like undergo the 1-4 conjugate addition, like to the that's connected to the beta carbon. While as here for stereochemistry, any existing like chiral centers, like in the molecules, they such as like the alkyl side chain, like one on the alkyl side chain, it ends up being like um it ends up remaining like unchanged throughout like the whole like mechanism. So it's just so its configuration is just like the same. Now for the oh, this is like a continued part here. I'll just leave that. But yeah, this is basically everything I just talked about. Now for the summary, to end it off here, just talking about everything. The the hard nucleophile basically attacks the carbonyl carbon in order to create the tetrahedral intermediate, and this carbonyl basically reforms in order to like kick out the leaving group. And with that, the acidic workup formation ends up neutralizing the system in order to yield and create the final ketone product. And yes, that is my presentation. So thank you so much for watching.